Rohit Bhattacharya with us today. Rohit is an expert in graphical models, and that's also the topic of this second part of today's workshop. He trained with one of the big minds of graphical models in causal inference, Ilya Spitzer, at Johns Hopkins, where he did his undergrad and his PhD. And now Rohit is an assistant professor at Williams College, where he, among other things, teaches courses on this topic. So thank you very much, Rohit. And in this session, Thomas Richardson will chair it. So when Rohit has finished before the first break, Thomas will maybe give some comments and let other people also ask questions, and he'll do so at the last session as well. So, welcome.
Thank you, Mats, and thank you to the organizers for this beautiful program. I mean, I've been here a week. It's been really amazing being at this institute. It's my first time in the UK, and there's a lot of UK culture that I have imbibed growing up in India. So I'm excited to be here in person witnessing it. Okay, so this is about identification, non-identification, and parameterizations of causal graphs with hidden variables. This is actually kind of ongoing work. I mean, teaching, I think, is just in general ongoing work. But this in particular, some of the concepts in this talk come from talking to my two undergraduate students, Juan Mendez and Hadassah Lurbur, and Zach Woodowdy. Zach's at Northwestern University. He also teaches a bunch of courses in causal inference. And the way that this came up was that I gave Juan and Hadassah some project in causal. I can't even remember what the project was at this point. And whenever I have a new research student, I give them a little boot camp of what causal graphs are, how do you do identification in causal graphs. And the question they asked me was, this is all well and good, but how do you know something is not identified? And I said, that's a good point. And I showed them a counterexample where if you have certain structures, you're not able to get identification. And they said, is that it? And I was like, well, yeah, I could give you another counterexample if you like. And they didn't enjoy the other counterexample either. They thought it was very, special niche cases. And so what I then told them to do is, well, I'll give you a tool. I'll give you some tools. I'll give you a framework. And why don't you give me proofs that you think is satisfying from your perspective for identification and non-identification? So this is some of where this comes from. This is, again, kind of ongoing work. I hope to get feedback on this work while I'm here and try and develop it further. So Juan started as a first-year student. He's now a graduating senior, so that gives you a sense of how long I've been thinking about this. So it's about three years so far. Okay, so what I'm going to cover, I'm going to be covering causal graphs with hidden variables. We'll be talking about identification and non-identification, and then I'll be talking about one of my favorite concepts in causal inference, Verma constraints, which are generalized equality constraints that do not resemble ordinary conditional independences, but do resemble conditional independences in special post-intervention distributions. Okay, so why non-identification? It's not usually a topic that's covered very much. I think non-ID proofs are underrated. Why Verma constraints? I think these are also understudied, especially in the context of estimation. Because unlike inequality constraints, Verma constraints do restrict the tangent space. So if you're familiar with semi-parametric estimation, you can use restrictions on the tangent space to gain efficiency in your estimators. I think it's quite underexplored what you can do with Verma constraints in that context. Okay, so why do I think non-ID proofs are underrated? Besides my students telling me that they don't believe my non-ID proofs, well, not that they don't believe it, they don't think they're very interesting. Here's a quote from a paper that was published at ICML. This is in relation to this, there was a paper that came out about 6 or 7 years ago at this point called The Blessing of Multiple Causes, which gives you some ideas for how you can get around the problem of confounding. And there were several follow-up works. This is one follow-up work that says Alex Demore, who wrote some comments about the deconfounder paper along with many of us in the causal community, raised some concerns about identifiability of the mean potential outcomes using the deconfounder framework in the static setting. But they sort of say that, okay, but these were pathological examples where identifiability might not hold. In practical settings, the outcome estimates from the time series deconfounder seem to be just fine. And so this is, again, why I think non-identification is underrated. It's like, well, we give you these proofs, but if you don't believe these proofs, or if you think they're pathological, then maybe it made me question, like, are we the baddies to some extent? This is also, this is David Mitchell, who's in several British panel talk shows. I guess a good meme for what's going on in America right now. So are we the baddies? So it's like, yeah, maybe we should do kind of a better job at explaining non-identification, try and make it a little bit more believable. So just to give you a sense of what I'm talking about, so to establish non-identification, it's sufficient to construct two causal models, M1 and M2, such that they agree on the observed data distribution. So I'm using this very simple example where I have a treatment A, an outcome Y, and some unmeasured confounder U. So my observed data distribution is just on A and Y. So I just need to construct two causal models that agree on that observed data distribution, but they disagree on some causal parameters. So in this case, I could say they disagree on the distribution of Y had I intervened on A and I set it to 1. So this is, I'm using Y superscript A1 to denote the outcome had I intervened on treatment and set it to be 1. Okay. And I won't name where this proof comes from, but here is a proof that tells you, okay, here are two causal models. So here's the first one. It's just a set of structural equations in this case. So one way of describing the causal model of a graph is through structural equations, where you just elicit a data generating process, and then you're allowed to intervene on these structural equations with what Perl would call the do operator. So here's the system. So U is just a coin toss. So it's just 1 with probability 0.5, 0 with probability 0.5. A is just equal to U, so A deterministically takes on whatever value U takes on. And then Y is equal to A XOR U. So that's the exclusive OR. For those of you who are maybe unfamiliar with the exclusive OR, so this is the truth table. So for 0 and 0, A XOR U is also 0. For 0 and 1, it's 1. For 1 and 0, it's 1. For 1 and 1, it's 0. So it's only when the two values differ do you get a 1, otherwise you get a 0. So you can see that because A is deterministically equal to U, A XOR U will always give you 0. So what that means is that in this distribution, or in this model, Y is always 0. Okay, so that's the first model. In the second model, the first two structural equations are exactly the same, but instead of going through this effort of defining Y to be A XOR U, I just say Y is equal to 0, deterministically. So obviously, these two models agree on the observed data distribution. I get that P1 AY is equal to P2 AY for all values of A and Y. However, if I go ahead and intervene, so if I say, okay, A is no longer just U, so I set A to be 1, now Y has a 50% chance of taking on value 1 in this model, 50% chance of taking on value 0. So that means that this causal parameter is 0.5. But in this one, since Y is just always equal to 0, the probability of YA1 equals 0 is actually just 1. Okay, so they disagree on the causal parameters. And that's the whole proof. And when I showed this to my students, they were like, is anything, in the real world, do you ever see XORs? And they had a bunch of questions. There's also positivity violations, as you can notice over here, because in both these observed data distributions, Y can never be equal to 1. So this requires some post hoc smoothing over the positivity issues. This is roughly how non-ID proofs typically go, and when we do something more complicated, we do use the XOR operator a ton for all of these non-identification proofs. But I should also say, feel free to ask questions as I go. You don't have to save your questions for the end. Okay, so we've modernized identification theory using modern definitions of causal graphs that mix potential outcomes, so things like single world intervention graphs by Thomas and Jamie, the Poe calculus by Jan Malinsky, Ilya, and Thomas. And I think it might also be worth our time to modernize some of this non-identification theory that uses potential outcomes notation as well. And because I think that provides some insight into what things are not identified, why they're not identified. It may inform some downstream sensitivity analysis if you're able to phrase it in this way. And so using some of that modern machinery of how do you define causal models or causal graphs in a potential outcomes while mixing in the potential outcomes framework, and then also these modern parameterizations of causal graphs with hidden variables. And that'll be a decent part of this talk is actually, we typically just think about the definition of the model, but we don't often parameterize it or talk about how you actually fit parameters from data. So I'll be covering a little bit of that, not in the estimation sense. There's going to be a whole tutorial about non-parametric estimation tomorrow, but at least telling you about what the MLE would look like, or if you were to fit these parameters. Okay, so the good news is that modernizing this stuff is possible. And in fact, at least the foundational stuff for doing so already exists. But the bad news is that it does require a lot of setup. And so I'll be subjecting you to some of that setup, which gets me to this example, initially without graphs. And I thought it was a simple example, and then I went back and I was like, no, I don't think it's actually that simple. So I struck that out. Okay, so just a few definitions, and this actually is reminiscent of how we define stuff in the missing data world, so I also work on missing data graphs. But I'll call an observed data law just a distribution over observed random variables. And here's an observed data law that's defined over two binary random variables, a and y. And for each combination of values that they could take on, so 0, 0, 0, 1, and so on, I just assign a probability. So P1, P2, P3, and P4. And in fact, I only need to specify 3 of these, because, of course, probabilities need to sum to 1. Okay, I could also parameterize this in a different way. So by the chain rule of probability, I have that this is equal to P of A times P of Y given A. So we can also specify this joint distribution in terms of the marginal P of A and a conditional P of Y given A. And here's what those two probability tables would look like. So I have the probability that A is equal to 0, and then I specify a probability that Y is equal to 0 given A is 0, and a probability that Y is 0 given A is equal to 1. And this is maybe the more natural parameterization that you all are more familiar with. The nice thing about this parameterization is that it's variation independent, meaning that I can specify all of these 3 numbers without paying attention to what the values of the other number is, because if I specify some value of P of A equals 0 that does not in any way restrict the other 2 numbers, this parameterization is variation dependent, meaning that if I specify one of these values, it does restrict the others in some way, because the probabilities have to add up to 1. And so that'll be, I'm just trying to get you used to the fact that there are multiple ways to parameterize a joint distribution, and that'll be kind of a recurring theme that shows up in this talk. Okay, all right, so the full data law then is the distribution defined over observed variables and potential outcomes. And so here's a full data law that's defined on the observed variables A and Y, and defined on 2 potential outcomes, YA1 and YA0. So the value of Y, had I intervened on A and set it to 1 and set it to 0. If I consider these all to be binary variables, this requires 15 parameters, 15 probabilities that I have to specify in order to get a full joint distribution over all of these. So that's like for all possible combinations of 0, 0, 0, 0, 0, 0, 1, and so on. I enumerate all those possibilities. Okay. So I'll say the full data law is identified if there's a bijection between parameters of my full data law and the observed data law. That's just a definitional concept of what identification means. If I get a bijection between these two, then I am identified. Now, of course, if you stare at these 2 distributions, this has 15 parameters, this has only 3 parameters. You cannot get a bijection between the 2. And so we're all aware. Oh, did you have a question?
I just wanted to ask, so is y related to ya?
Not yet.
Okay, it's not.
Yeah, not yet. So this is like, if I just specify a full data law and I've made no assumptions about it, I would have 15 parameters. And yes, okay. So without assumptions, causal inference is impossible, and this is a very easy demonstration of why. 15 cannot be mapped to 3. Okay, so by the chain rule of probability, though, I can start to decompose this full data law. So I can say that, okay, it's the marginal distribution of the potential outcomes, and then I have the treatment given the potential outcomes, and then I have the observed outcome given everything else. So this is just applying chain rule of probability. And now I can start to impose restrictions that might give me identification. Okay, so the first restriction, so this is to Thomas's point, first thing I can assume is consistency. I can say that the observed value of, the observed variable y is just a deterministic function of the treatment and the potential outcomes. So when a is 1, y is equal to ya1. When a is 0, y is equal to ya0. And so what that means is that this is just now completely deterministic. And so this conditional is actually uninteresting. Because it's fully deterministic, I don't need to specify anything about that joint distribution, or that conditional distribution, sorry. Okay. Second assumption I can make, ignorability. That cuts out the potential outcomes from this conditional distribution. And then I'm going to make a third assumption that will make people unhappy, a cross-world independence, and we'll revisit this in a second, which then says that the joint distribution over the potential outcomes factorize into these marginal probabilities. And so if I now count the parameters, I get, okay, this is just a single marginal distribution over a binary random variable. So that's one parameter. This is one parameter. And then this is also one parameter. So now I'm in business. I get to start, I can start to get a bijection between my full data law and my observed data law, which also had just 3 parameters. Okay. So under these 3 assumptions, we can have hope of a bijection. So in particular, let's just do it. So how do I identify P of A? Well, P of A equals 0 is just equal to P of A equals 0. It's pretty good because that's the easiest identification argument I can make. P of YA1 by independence, in particular ignorability, is equal to P of YA1 given A is equal to 1. And then by consistency, this is just equal to P of Y given A equals 0. Oops. Y given A equals 0. Oh, never mind. That's okay. You get the point. And then you can see that this is the bijection we end up with. Okay. And so what you'll notice is that I've got marginal probabilities on the left, and this is the natural parameterization of the joint distribution over A and Y on the right. So I have P of A equals 0, P of Y given A equals 0, P of Y given A equals 1. Okay. All right. So let's revisit that cross-world independence that we did not like and get rid of it. So if we get rid of it, this no longer factorizes. So I'm back over here, where I just have a joint distribution over both the potential outcomes. And now I need 3 parameters for this, and I need 1 parameter for this. So I have 4 parameters in my full data law. So something must be not identified. The question is, what is not identified? So under ignorability and consistency, I can say P of YA1 is still equal to P of Y given A is equal to 1. So that's still true. P of YA0 is still equal to P of Y given A equals 0. But these 2 parameters alone don't form a full joint distribution. So the question is, what is the remainder thing that I can say is actually not identified? So like what is the joining term that would tell me that I have a non-identified parameter here? Okay, so what I'm going to use is something known as the Mobius parameterization to disentangle identification and non-identification. Okay, so of all the things that I've learned since I started causal inference, the thing that surprised me the most is just how many ways you can parameterize a joint distribution. So of course I've shown you, if I just give you two binary random variables, you can directly specify the three joint probabilities, or you could specify a marginal probability and then two conditionals. It turns out you can also specify two conditional probabilities. So I could specify x equals 0 given y equals 0, and y equals 0 given x equals 0, and then a joining term. And I'm not sure of how far back this goes, but at least since 2007, Chen had a non-parametric way of doing this. So I'm mentioning everything in the binary setting just for simplicity. This is all, it actually applies non-parametrically. There are parameterizations that you would basically specify f of x given y equals 0, f of y given x equals 0, and then a joining term. And I'll get into a moment what that joining term is. And then you can also specify two margins and a joining term. So rather than having conditionals in a joining term, you specify margins. And this has a longer history as far as I can tell. So it goes back to 1964. There was a paper by Plaquette where he tells us how to parameterize these things. Okay. All right. So here's how you do it for binary variables. So if you specify two margins, p of x equals 0 and p of y equals 0, the joining term in this case is just the joint probability of both of them being 0. And then how do you derive the rest of the probability table? So 0, 0, that's obvious. It's just p of x equals 0, p of y equals 0. 0, 1. This is, so if I just shift stuff around, so what this is saying is that p of x equals 0 and y equals 1 is equal to this. So if I just move this to the left-hand side, that's just law of total probability. The p of x equals 0 should be the sum of those two terms. By symmetry, this is the same thing. And then I love it when things kind of line up nicely with really simple concepts that we've learned about. So for this, this last term, so you can say that p of x equals 1 and y equals 1 is equal to 1 minus, oh geez, let me write it here. Okay, p of x equals 1 and y equals 1 is equal to 1 minus p of x equals 0 or y equals 0. And then, so this stuff that you see here, of p of x equals 0 plus p of y equals 0 minus p of x equals 0, y equals 0, that's just the inclusion-exclusion principle. Right? So you can rewrite this guy as p of x equals 0 plus p of y equals 0 minus p of x equals 0 and y equals 0. Okay? All right, so that's how you get a full joint distribution, just using these three parameters that folks don't often use, but I think is very useful. Okay, so how do you do this in general for k variables? So you would specify univariate margins. So you would specify all variables being just equal to 0. You would specify bivariate margins, so all pairs equal to 0. You would specify trivariate margins and so on until you get to the k variable margin, so all of them being equal to 0. And then the general rule is given by what's known as Mobius inversion. So if I had a query of what is p of v being equal to some value little v, that's given by the Mobius inversion lemma. Yes, okay, before I move on. So some of these margins could simplify if you have independence restrictions, and we'll get to independence restrictions as we start to talk about causal graphs. So for example, if you have vi being independent of vj, this bivariate margin would just simplify it into, it would factorize. Okay. So if I give you the Mobius parameters M for a distribution P of V that has no constraints, maybe I say M square bracket C is the specific Mobius parameter for the margin C that's some subset of V, and we'll say trivially M empty set is equal to 1. Then to get P of V equals V, this is the formula that you would use. This is just actually, you can really think of it as a very elaborate version of inclusion-exclusion applied several times. And you can see there's like an alternating sum going on depending on the size of the margin that you're dealing with. And then you're using some of these parameters in that alternating sum. Okay. And what are the sets that are involved in the alternating sum? So you first tell me what the set of all the variables that are being set to 0, and then I take all supersets of that that are also subsets of all the variables. All right. And then you could do a quick sanity check over here. So for example, if I'm interested in what this formula has to say for P of x equals 0, y equals 0, so in this case, the only superset of that is the case where I have both x and y, because everything is being set to 0 here. And so of course, this formula just says that this should just be equal to P of x equals 0 and y equals 0, sort of by tautology. It's not a very interesting one. Okay, and then the interesting one, let's just do this guy over here, P of x equals 1, y equals 1. So in this case, every possible set that's a subset of V is actually a superset. So over here, the variables that are set to 0 is the empty set. So no variable is set to 0 here. So the supersets of this are the empty set, just x, just y, and x and y. And so if I apply the Mobius inversion formula, I get the empty set gives me a 1, and then I get these two singletons, so that's minus P of x equals 0, minus P of y equals 0, and then this is a plus P of x equals 0, y equals 0. Okay. All right. So back to our problem. We did a lot of setup. What does this buy us? So we talked about how this no longer factorizes. This has 3 parameters. This has 1 parameter. And now we can use the Mobius parameterization to disentangle the ID and non-ID pieces. Okay. So we're going to parameterize this guy in particular using the Mobius parameterization. And so what that gives us is, okay, I've got P of A, which is identified. I've got the margin, P of YA1. I've got the margin, P of YA0. And then I've got the joining term where both potential outcomes appear and they're being set to 0. And I have a bijection for all of the single world parameters to the observed data parameters. So remember, the observed data only has 3 parameters. We have 4. And so this sort of proves that the only thing I can't identify is this cross-world parameter. And not only that, it allows me to introduce a, as Ilya was just calling it, a dense set of counterexamples. So rather than having that specific counterexample where I was using the XOR operator, here's how it would work. So I specify the margins. So I can specify any 2 values for y is equal to 0. And I'm sorry, this should be YA1 equal to 0. So let's say I pick 0.3 and 0.4, just any arbitrary values. And then any value of this that gives a valid joint probability distribution constitutes a counterexample for why your full data law is not identified. And so for example, I could pick 0.2, I could pick 0.3. But one thing to note is that you do have to be careful about how high you can go. So actually you can do, I should say 0.2 and 0.1. You shouldn't go to 0.3 because you'll notice that these parameters are variation dependent. So once I specify these two, it does restrict the values that I can pick for the join. So otherwise I get an invalid probability. So if I, for example, pick this to be 0.5, 0.3 minus 0.5 would be negative 0.2, so I end up with an invalid probability. But literally any value that gives you a valid probability distribution. All right, I'll pause there for questions. Okay, so then let's move on to causal graphs. And because now we know that cross-wall parameters are not identified, we can now discuss identification and non-identification of single-world parameters. Okay, so we'll start with statistical models. So what's a DAG? A DAG is just a graph with directed edges such that there are no directed cycles. So, for example, this is a DAG. However, this is, running out of space here. This has never happened before. Okay, but this is not a DAG. And then a statistical model of a DAG is the set of distributions that satisfy what's known as the DAG factorization, which is that you take the joint distribution and you get a Markov factor for each variable given what are known as its parents. So the parents of A over here is the empty set, the parents of B is A, the parents of C is A and B. Equivalently, you could say that is the set of distributions that satisfy the global Markov property with respect to G. So for disjoint sets X, Y, and Z, we have that D-separation in the graph implies independence in the probability distribution. And I'll assume, given the audience, that everyone knows what D-separation is. Okay. Then I'll talk about statistical models of an ADMG. So an ADMG is a graph with both directed and bidirected edges, such that there are no directed cycles, and you can have at most one directed edge and one bidirected edge between each pair of vertices. So for example, this is a valid ADMG, and actually a very famous ADMG. This is a observed data representation of the IV model, which I'll talk about latent projection in a second, but here's this ADMG is kind of representing that unmeasured confounder between B and C. So you are allowed to have more than two edges between variables as long as one is directed, one is bidirected. Okay. A statistical model of an ADMG is the set of distributions that satisfy the nested Markov factorization with respect to G. I will not go into the entire nested Markov factorization, but I promise I will give you an example of what the nested Markov factorization looks like. And I'll do it using the front door model. Okay. The nice thing about the nested factorization is that when you have a distribution that nested Markov factorizes with respect to an ADMG, it implies an ordinary global Markov property. So I'm saying ordinary because this only lists conditional independence constraints. It doesn't list Verma constraints. And what it says is that for disjoint sets X, Y, Z, we have that M separation in the ADMG implies independence in the probability distribution, and other equality restrictions we'll get to. But M separation just generalizes D separation in I think, a fairly straightforward manner. So a collider in a DAG is just two directed edges meeting at a certain variable. A collider in an ADMG is, you can also have them mixed with bidirected edges. So one directed, bidirected, bidirected, directed, or both bidirected. Okay. But otherwise, the definition is essentially the same. Okay. So on to causal models of a DAG. So how do we form a causal model of a DAG? The first thing is you start with a DAG. So there's 4 steps. You start with a DAG. You define one step ahead potential outcomes. You pose an independence model for these one step aheads, typically NPSEMIE or Fristig. finest fully randomized causally interpretable structured tree graphs. And then other potential outcomes are defined in some manner, in particular recursive substitution. And this also provides a link to the observed data, or the observed random variables. Okay, so start with a DAG. This is a really nice looking DAG. It's the conditionally ignorable model. And then the next step is to define the one-step aheads. So the one-step aheads basically say, for each variable in your DAG, you define a potential outcome, or rather a set of potential outcomes of the form vi, and what would have happened to vi had I intervened on all of its parents and set them equal to some value. And so in this case, I have c, a, and y. And so the one-step aheads are, well, what would happen to a if I intervened on c? So again, if I assume binary random variables, there's two of those potential outcomes. And then what would happen to y if I intervened on c and a jointly? And there's 4 potential outcomes for those, corresponding to all combinations of assignments. Okay, so we have our one-step ahead potential outcomes. The next step is you pose an independence model on your one-step aheads. You have 2 typical choices. One is Perl's NPSEM-IE, which stands for non-parametric structural equation model with independent errors. And what that says is that each set of the one-step aheads, rather, are independent from each other for all possible values of treatment assignments. The Fristig model is slightly weaker in the sense that it imposes less independence restrictions. What it says is that this independence holds only when the treatment assignments agree. So you cannot have cross-world independencies. Okay, so what you'll notice about both of these is that neither of them actually propose any conditional independencies. They're actually all marginal independencies. They're all of the form x independent of y. There's no independence that looks like x independent of y given z. And so the nice thing about that is that since they're all marginal independencies, a marginal independence model can be faithfully represented using bidirected graphs. This is actually a big impetus in Shigian's latest paper. Yeah.
I mean, are they really though? Because your conditional distribution are indexed by the value. These also seem like they're indexed by the value. And if you're going to try to go graphical here, it's not going to be purely a bidirected graph. You're going to have to represent the indexing, right? So it's going to be like a conditional bidirected graph or whatever, right?
Yes, that's where the recursive substitution and consistency will come in. Yeah.
Okay.
Yeah.
Just your first condition, there's a set on both sides, right? It's sets of.
Yeah. These are sets.
It's not like one random variable.
Yeah. Sorry, it's
not in the same.
Yeah. Okay. So just to get a sense of what those restrictions might look like, this is what the NPSEM-IE would say about independence restrictions among the one-step aheads. So you see that within each set of one-step aheads, so over here I have this is essentially a cross-world joint distribution. This is also, cross-world. And so there are no independencies within these one-step aheads, but there are a bunch of independencies between one-step aheads. So in particular, I have that C is independent of both AC0 and AC1, which is in turn independent of YC0, YC0, A0, all the way up until, oh, Jesus Christ, YC1, A1. Okay. Now, for an example of how the Fristig model relaxes some of these constraints, here are 2 edges that you would have in the Fristig model, but not in the NPSEM-IE. So you can see that AC1 and YC0A0 disagree on the assignment to C. So you would add a bidirected edge between those two to indicate that they are not independent of each other. And similarly, you might add a bidirected edge here, and then a bidirected edge here. Oh my goodness. Oh, you get the point. AC0 and YC1A1. Okay. Okay, but that's a lot of edges to draw, so I'm just going to use NPSCM IE for the remainder of the talk. The main difference that comes about with respect to identification is actually about when it comes to mediation. As far as I know, for average causal effects that do not talk about mediation or don't talk about nested counterfactuals, NPSCM IE and Fristic gives you the same identification and non-identification results. Okay. Okay, the last step is that you have to define other counterfactuals, and you need to link to the observed data. And that's done via recursive substitution. So let's say for some subset A that you're treating as that you're using as your treatment, we'd like to know what these models say about the potential outcome VIA. So what happens to VI when I intervene on A and set it to equal to little a? And in particular, A may not be equal to all the parents of VI. So far, we've only said what happens when I intervene on all of the parents of a variable. And that's given by this definition of recursive substitution. It's a very nice, pleasant definition that says VIA is defined recursively. So you look at all the parents of VIA. You look at all the parents of VI. If the parent happens to be in the treatment set, you set it equal to whatever value has been specified. And if it's not in the treatment set, you recurse. So you call the definition again in order to determine what exactly it's equal to. And the reason this recursion terminates is because the DAGs are acyclic. So eventually, you'll reach a variable that has no parents, and so you'll stop. Okay, we have a little bit of time, so maybe I'll show you the code. As a computer scientist, I don't believe things until I actually implement it. And so you can implement recursive substitution pretty easily, it turns out. And I will do that very, very quickly. So what I have here is and if you, I think you have access to the slides, so you have access to this code. What I have here is a very minimal DAG class that just tells me, it's just got a function that tells me what the parents of a variable are. And then I'm going to define recursive substitution. I did find the definition of recursive substitution a little bit misleading in the following sense, in that it usually tells you, okay, here is a set of values for what the treatments are going to be assigned to. But I think, for me, it's more precise to say it's a mapping, so it's you get what variables are being intervened on and also what values they will take on. So, so it takes in VI, the variable. It takes in a treatment map, which is, so for example, I could say, I'm intervening on A, setting it equal to little a. I'm intervening on M, setting it equal to little m, so that's a map. And then it also takes a graph because you need to know what the parents are. So recursive substitution also relies on the graph. Okay, so all recursions have a base case. The base case is if VI has no parents, I'm done, I just return VI itself. The recursive case is so I'm going to go over each parent of VI. So I'm going to go over all of the parents of VI. And then I'm going to say whatever treatment assignment I'm supposed to have for VJ, if VJ happens to be in the set of things that I'm intervening on. Else, I call the recursion with VJ A map in G. Oh no. Okay. And then this is just a fancy way of just returning the. I'm just formatting the potential outcome. Okay, so we're gonna see how recursive substitution works for this graph. So it's just a to m to y. So if I ask for the definition of the potential outcome using recursive substitution for MA. MA is just a one step ahead, so this should just return MA itself. Since recursive substitution should imply consistency, when I ask for what happens when I intervene on nothing, it should give me M parentheses capital A, the definition of consistency. And then because this has an exclusion restriction, if I ask for YAM, it should give me that that's just equal to ym, for example. Okay. So now if I run that and run that, you can see that, yeah, that's exactly what we get. Yam is just equal to ym. Ya is equal to m parentheses a. So this is sort of the interesting one. I want to know what happens to y if I intervene on just a. Well, that's y. And you sort of have this nesting where you say, well, you first need to look at what value m would take on when you intervene on a, and then feed that into y. Okay. Right. Usually very comfortable live coding in front of my students, but this is a very different audience. Okay. And so once you have all of that, that sort of licenses you to put these directed edges that go into the observed variables from your one step ahead. And these edges are now really just consistency preserving edges. So this is sort of saying that when c is equal to 0, a will be equal to ac0. When c and a are both equal to 0, then y will be equal to this potential outcome. And if a and c are 1 and 1, y will be equal to this other potential outcome on the top right. Okay, so this is sort of the full model. And what I've mentioned at the start of this talk is that really what we're interested in is single world parameters now, because cross-world parameters are just not identified, usually, unless you make some very strong assumptions. And so latent projection is a way of studying the margins on various variables. So if I want to study the margin of an ADMG, so let's say I want to study O, which is some subset of V, the rest of the variables could be considered latent. And then it turns out the margin, P of O, is also satisfies the nested Markov factorization according to an ADMG with vertices O, and these are obtained by what's known as the latent projection operator. That was defined by Verma and Pearl in 1990, but this result in particular was shown in the nested Markov paper. Okay, so here's how latent projection works. So if you have an ADMG with these vertices, so O union L, and you want to project onto just a subset O, you have OI to OJ in GO, if and only if there's a directed path from OI to OJ in the full ADMG where all of the intermediate variables are in L. So just as a concrete example, if I have something that looks like this in my original graph, and I'm latent projecting L1 and L2, I would end up with an edge OI to OJ in the latent projection. However, if I had like an OK in here, I don't get OI to OJ. Right? So every intermediate variable has to be latent. Okay, and then the rules for a bidirected edge are you essentially have something that looks like a backdoor path. And so, for example, if I have OI bidirected L1, should use the left side more, I think. Okay, if I have OI bidirected L1 going down to OJ, this will give me a bidirected edge OI bidirected OJ. And so all intermediate vertices need to be in L, and there should be no colliders along the path. Okay. So if we're thinking about margins of the full data law, that's what the full data law looks like. Here's what a single world margin might look like. So I've latent projected out everything except some potential outcomes that agree on the value assignments. And it turns out that the latent projection here is kind of trivial because in an NPSEM IE model, there's not very many bidirected edges going around, so you basically end up with a DAG in this case. And then if I project further, so I get rid of all potential outcomes, I end up with just the observed data log, which is the initial DAG that I started with when I was defining this model in the first place. Okay, and here's a single world template that you could define. And so this is, reminiscent of swigs, but not quite a swig. But over here you have just AC for some generic value of what I'm intervening to, and YCA, which is again generic. And if I want to do identification of the full law, it turns out, so I have P of C equals 0, which is just equal to P of C equals 0. It's pretty easy. P of AC, which by independence is equal to P of AC given C is equal to little c. And then by consistency, this is just equal to P of A given C is equal to little c. And then you have P of YCA, which is equal to, again, by independence, YCA given A equals A, C equals C. And that is equal to P of Y given A equals A and C equals C. So you end up with a full bijection on the single world parameters. So, so all single world parameters end up being ID, and this is the mapping. And you can kind of see these are pieces that eventually lead to the G formula. So if you want the G formula, so if you want PYA, by recursive substitution, that's equal to PY capital C and A. And then you can marginalize over all possible values of C. This is what you end up with. Then you use independencies in the graph to say that C is independent of YCA. And then you just use this guy, you plug in this guy, and that gives you the G formula. Okay. All right. So now the interesting things start to happen when we ask things like, what happens if your Fristig assumptions or your NPSEM IE assumptions don't hold? And what I mean by that is not stuff involving cross-world quantities, but just involving violations of the single world assumptions that these models make. So for example, the NPSEM IE would say that, well, if I start with a DAG that's just A to Y, I would have these two potential outcomes, and of course these are linked together, and then I have recursive substitution giving me these links. However, what it wouldn't say is that A and YA0 are correlated, for example. Okay. So now if you start to make those correlated, then your observed margin ends up being not a DAG. So now this is known as the Bow-Arc graph. So if I have that A and YA0 are confounded, I may end up with non-identification again. Okay, and so in such cases, identification of all single world parameters may not be possible. So it could be that you could get identification, but in some cases, if you have enough other information, so for example, if you have something like a front door graph, which I'll talk about in part 2, you might end up with identification. Okay. So I've got 5 minutes. Okay, so if I want to prove that this Bow-Arc graph is not identified, I need to do some work in order to show it. But I've already given you, so this goes to the first task that besides the cross-world stuff, this is the first single world parameter we're going to show is not identified. So if all you have is this, it's kind of easy to show that PYA0 is not ID. And the way that we're going to do it is we're going to break this up. So you'll notice that I got rid of some edges. In particular, I got rid of the cross-world edge and I got rid of this edge, and I'm moving to a submodel, just to say that I know cross-wall things aren't identified, so I'm just going to rule that out, and then if I can show that it's not identified in a submodel, it's definitely not identified in a supermodel, because the submodel is just a special case of it. Okay, so over here, I can say that PYA1 is still identified. So this is just equal to PY given A equals 1. This guy's okay. I can also say, so now notice that I have this joint over P of A and YA0, and I'm going to apply the Mobius parameterization again on this joint. So what are the Mobius parameters of this? It's P of A equals 0, which is identified. That's just a function of observed data. No problem. I have P of YA0 equals 0. And then I have the joint probability P of A equals 0 and YA0 equals 0. This joint probability is actually identified just by consistency, because I have A being equal to 0. I've chosen a very convenient reference value here. I've done it intentionally to say that this is ID, this is ID, and this is ID. Now, if you think about what the observed data is, the observed data is just A to Y, A bidirected Y. That's 2 binary random variables. I can have at most 3 parameters on this joint distribution. So I've already kind of exhausted all of the information in my observed data to identify this guy, and this guy, which must mean that this is not ID. Okay. So let me show that to you just more explicitly. So this is ID, this is ID, this is ID. They have some bijection with observed data parameters. That must mean that this guy is not ID. And in fact, you can construct, again, in a really dense set of counterexamples where you specify P of A equals 0, you specify this joint probability, and then you can do whatever you like with PYA. Oh, I'm sorry, this should have been PYA0. Questions? Yes?
Can you please just repeat the argument of why then this expression is not identified?
Yes, okay. So identification is about forming a bijection. And I have 4 parameters in my full data law. And I have 3 parameters in my observed data law. Yes? And so I'm arguing that 3 of the parameters in my full data law are accounted for, which are P of YA1, this joint probability, and P of A equals 0. So because 3 of them are accounted for, that must mean my 4th is the thing that's not identified. And that's the one that I have some freedom. This is my degree of freedom. I can give it whatever value I want. It will agree on the observed data distribution. Oh, I got a minute, but I'm gonna, yeah, maybe this is a good stopping point, because, yeah, then we get into identification with unmeasured confounders and stuff.
Any other questions?
Yes?
In the first part, you mentioned the cross-world independence assumption, and kind of said, well, great if you can make it, but that's actually not applicable. But what if we consider a scenario where the variable A includes all direct causes, and assume we have reason to believe, indeed, there aren't any more? Would you then not consider it a reasonable assumption?
So at least the philosophical reasons that are given for cross-world, not having any cross-world assumptions, is that even if you were to be able to have infinite power, you can't test a cross-world assumption. You can't run the experiment to test cross-world assumptions. So I think philosophically, that's why people are opposed to it. If there's strong reason to believe that you can make it, I personally don't make cross-world assumptions, but I understand that once you make them, you can get a lot of identification. But yeah, I would say that's probably the argument.
Okay, I just took me a while to reflect. I guess this was the example you talked about the joint and the marginal, right? So
Yeah.
they are naturally variationally independent, these four parameters. Those are the four parameters.
Oh no, they're variationally dependent.
Okay.
Yeah. These, because these are Mobius parameters, they're actually variationally dependent. So P of A, that margin, P of y A0, and then the joint of A and y A0 are actually variationally dependent.
But sort of more generally, do you have to be careful? You're making this argument about, like, you have, in the observed data, you have 3 parameters, right? But then here you have 4. I guess you would have to be a bit careful about the variational dependence, right? Because if 2 were just equal to one another, then that's...
Yeah. So if I go back to like this concrete example with the cross-world stuff, so it does restrict the range of values that cross-world parameter could take on, but like in a trivial sense. It's like any number that produces a valid probability distribution would be fine. But I agree, if you have like some determinism, that would probably lead to identification. That's kind of like, what is that assumption called?
Faithfulness.
No, not faithfulness. What is it like if you know one potential outcome, you can tell what the value of the other is?
Rank preservation.
Rank preservation, yes, thank you. Yeah. So that's kind of, if you have something like rank preservation, you can get extra identification.
So just one follow-up question here. So this is, I like the line of work. Is I think the first email exchange I ever had with Ilya was about whether or not examples of non-identification were too deterministic, so that people would find plausible. But I guess one thing is you could have a lot of distributions that are all counterexamples, but then if you present a whole series and they all give you the same value of the quantity that somebody cares about, and you vary something and the average treatment effect doesn't change,
Yeah.
the person's not going to be particularly excited, or is satisfied with that as showing up. So I guess one question I was thinking is, your activity seems closely connected to sensitivity analysis. So is that something?
Yeah, I'm hoping that if you do non-identification in this way, you start to like really pinpoint at what point your identification broke down, and then maybe you can start to, maybe it helps with bounds or partial identification, but also certainly sensitivity analysis where you start to vary the amount of confounding or, yeah.
No maybe about it, sir.
Any other questions?
Oh, yeah.
I'm having a bit of difficulty understanding the possible meaning of the spy-directed edge in the bow arc graph. Do you have a kind of practical situation maybe that would illustrate why one might expect such a confounder there?
Oh yeah. So this is like if you just have treatment and you have outcomes, so like say A is smoking, Y is lung cancer. There could be any number of variables that cause both A and Y, and so that would lead to the bow arc basically. So like age, income, genetics, what have you. So it's like the potential outcome would be correlated with the treatment through all of these unmeasured variables basically.
Okay, so then in a sense maybe your original DAC was kind of wrong already as well.
Yeah, so typically the way we go about it is that you specify identification algorithms take an ADMG as input. So you could specify the bow arc as an input and get as output not ID. But there are other interesting examples like the front door graph where, you have this bidirected edge between A and Y, but there's some other interesting structure that gives you identification, despite the unmeasured confounding.
Thanks.
Okay, we're a little over time, so I think it's time for a couple of things. Let's thank Rohit and